All right, so welcome, one and all. I would like to borrow your attention for a little while to discuss attention. This talk will be about the influential 2017 paper, Attention is All You Need. So in it, they describe an approach to machine translation that's based on the attention mechanism. Now, instead of talking about a bunch of history, I'd like to jump pretty much right into the contents of the paper. I'm going to be doing it in a different order than they do. So I will start with the task and ask, why should we be using attention? What is attention? How do we apply it properly to sequence translation tasks? How do we deal with the problem of positions, the multi-head attention mechanism, and finally, the full model in which attention is all you need. So the task. Oops. So our basic task is sequence transduction, the conversion of one sequence of inputs into another. In this case, we're going to be focusing on natural language sequences. Of course, lots of important tasks fit into this framework. The one that everyone, of course, uses all the time, I think, is machine translation. You might want to translate an English Shakespeare sentence into a German version of that sentence. Another more abstract application would be constituency parsing. So that's something where you take a sentence in a natural language and you convert it into a syntactical tree that represents the structure of the sentence. Another common task is text summarization. So that's a translation task from one language to the same language, in which you take a long text and you convert it into a short and pithy version that touches the major points of that task. And of course, there are lots of other tasks that you could look at. Now, for sequence-to-sequence translation tasks, until 2017, the recurrent neural network was king. Recurrent neural networks function as follows. So you have a recurrent unit, which maintains tensors that represent their internal state. And you take that and you pass it over the tokens in a second sentence or in a sequence. And as you input each token, you update the internal state of the recurrent unit. And when you get to the end of the sentence, then you have managed to provide a digest, an embedding of the meaning of the sentence into the internal state vector. This is very natural for a number of reasons. It mimics the way that humans process language. We perceive language as sequences. It allows an incremental synthesis of meaning. And if your recurrent units have a good memory, if they're able to remember things over long sequences, then it allows them to draw connections between distantly connected items. And if you want to do something like translate German philosophy, then you're going to, if you want to translate this sentence, then you're going to need a pretty good memory for your recurrent neural network. So that's a key aspect that's required, this connecting distantly connected items. Okay, so recurrent neural networks, they work quite well. People got good results for them. Why should we give them up? Why should we use attention? There are a number of reasons. One of them has to do with a limitation of a practical limitation of RNNs. So one problem with RNNs is what is the thing we just talked about. One of the best computational tools that we have available for training neural networks is the GPU. And the reason that it's useful is that it allows for massive parallel computation. However, RNNs are inherently unparallelizable objects. That's because RNNs process tokens in order. That cannot be made a parallel procedure. You can perform a lot of parallelization if you use a large batch size, but that will only go so far. If you have a complex model and you have a very long input, then at some point you'll start running into memory restrictions. What are some alternatives? Well, you have CNNs. CNNs have some examples such as that they are highly parallelizable. They are great for running on GPUs. However, what well, what are some of the other strengths of CNNs? They're used in image processing and sound processing. And one of their great strengths is their localization. They pay attention to inputs. The output is only sensitive to things that appear within a particular range of the inputs. That's great when you're looking at image processing, where you're mostly interested in local relationships. But in natural language processing, it becomes a problem because the receptive field of a convolutional network is proportional to a vanilla convolutional network is proportional to its depth, as you can see in this picture. So that means that if you want to perform sequence modeling on long sequences, you want to get these long distance connections, then you're going to have to use a very deep network. This can be helped with things like techniques like dilation, but it does remain a problem. Okay, so this is our situation with complexity for the two types of networks that we've discussed so far. So is there a better way? Now, of course, because you're here, you know as well as I do that attention is what's on the table. So what is attention? Attention is inspired by how we process information. We use attention when performing all sorts of tasks, that language, image, sound processing, and so on. When we process information, we don't treat all of our inputs equally. Instead, we want to determine what is relevant. We determine what is relevant, and then we take the relevant items and we synthesize them into some bigger picture. How do we determine what is relevant? Well, that requires defining a task. We need something for it to be relevant to. So for example, when we're looking at a sentence, we might want to find the subject of the sentence. At a picture, we might want to locate the mountain. If we're looking at sound, we might want to locate the phoneme. Okay, so that's a task. Now that's a very, what I want to say, abstract concept. In general, especially in computation, we need to make this more specific. So we need to actually identify criteria that are relevant to that define what the task is. So in a sentence, you might be looking at like which if you want to find the subject, you might want to know which words are nouns, where they are relative to the verb, does it come near the beginning or the end of the sentence, that kind of thing. So in image processing, let's say that our task is to find a mountain in an image. Then the criteria that we might be interested in are things like looking for a pointy top or a triangular shape. We might be looking for snow above a darker terrain. When we look at the information inside the image to try to determine what pieces are relevant, we're going to be using image features. That would be things like sharp angles. It would be things like sudden transitions in color in the vertical direction. Those are the types of things that you might get out of a few layers of a convolutional neural network. So now if we look for the image features inside this image that are relevant to the criteria that we have outlined, then we might end up with something like this. So we see a couple of regions where a couple of regions are being focused in on. We have one region over here, which is kind of mountain-like. It's kind of pointy and has some of this color variation, but it doesn't match the criteria very precisely. And then of course we have the mountain, which is exactly what we're looking for. So this is the type, this then would describe what data we want to actually, what data is relevant to answering the task that we have set. Now, another way of describing these terms is the criteria, that is what we want to know, what we're looking for. And then we have what we compare it to, that's the key. That's what we use to determine relevance to the criteria. So here we have our query and our key. Now, so far I've only talked about images and sound and stuff like that. Neural networks require vectors. So how do we simulate this concept of attention with a list or with a collection of vectors. And the approach that's taken is that you sum them up. You sum up a collection of value vectors. So these are the values that we're getting, that we're interested in collating. And we sum them up, but we weight them according to their relevance to the task at hand. So what are our inputs to attention? First of all, we have, what do I want to know? That's the query. We have, what do I use to determine relevance to the query? That's the key. And what do I want to summarize? Those are the values. And each of these are going to be vectors. So the query, if you have one question that you're asking, and you have one query, and that's a vector in a DQ dimensional vector space. You have a sequence of n pieces of data you're looking at. That means that you have one key and you have one value for each of the n pieces of data in that sequence. So keys live in a dk dimensional vector space, and the values live in a dv dimensional vector space. Okay, so here we have an example of a query, keys, and values. So we have one query, we have a sequence of keys and values, one key for every value. These keys and these values could be the same, but they may be different. So in this case, the keys and the values are different. Now, the next thing we need to do is we need to determine relevance. Now, what relevance is going to be is for every key, we're going to have a number that determines how relevant this vector is to this query. So here I've encoded this by different colors. Here, black means highly irrelevant, and white means very relevant. The next thing we need to do is we need to weight things according to that relevance. So we using these scores here, we rescale the value vectors to get a collection of weighted vectors. And finally, we take all those vectors and we stick them together into the final result. So that's the basic setup of the attention mechanism. Now, so far, I haven't really written any equations. So let's get more specific. So relevance. Relevance is a function which takes in a key and it takes in a query. And it tells you, given this key, so this is the ith key, given the ith key, what is the relevance score of that ith key to the query Q? So we have one relevance score for each of these n entries. This relevance score could be computed in many different ways. So the original version was concatenative or additive attention, which looks something like this. The one that's used in this paper, the attention is all you need paper, is basically dot product attention. This should be natural. So here, ki and q are similar if they're are going to be similar if they point in basically the same direction. So this is cosine similarity. They do use a slightly different version. They rescale it by the square root of dk. This helps keep the network from blowing up. But basically, we're using cosine similarity to determine relevance here. Once we've gotten the relevance scores, we then need to determine the actual weights. And this is done using, everybody does this using softmax. So as you all know, softmax, you have some scores. You take the exponential, and then you divide by the sum of the exponential. And this gives you a sequence of W's, W1 through Wn. They sum up to 1, so they're like a probability distribution on the list of vectors here. You weight the ith vector by the ith weight, and then you sum up all of the vectors, and you get one output vector. So let me emphasize this. If you have one query, one question you want to ask, then you're going to have one output vector. And that is the basic attention mechanism. This can be applied in this can and has been applied in lots of different places. Let's go back to our task then. We were talking about sequences. So far in discussing attention, we've had one query Q, and we've had a sequence of key value pairs, Ki and Vi. And we have an output, which is given the query Q, it's the sum of the V's weighted according to their relevance to the query Q, as measured by K. So here are our equations. Now, for sequence-to-sequence models, what we want to do is we want to take some input sequence, which has length n in, and we want to map it to some output sequence, which has length n out. More generally, we may have many different attention layers. Each one will map a sequence to a sequence. N in and n out may or may not be equal in that case. If we have n out outputs, that means that we need to have a query for each output. So here we have n out queries, Q1 through Q sub n out. This means that we have to modify our equations somewhat. This is easy to do. You add an index a to the Q. So here A goes from 1 to n out. Add an index A to the Q, and then you just follow through the A's in the equations. So it appears here in the relevance score. The relevance score appears in the weight. So we add an A to the R's, we add an A to the W, and the W appears here. So we add an A to the W, and we add an A to the O. So this gives us 1 through n out output vectors corresponding to our queries. And in general, of course, models are going to be built from stacks of attention layers on top of one another, mapping sequences to sequences many times. Here, I've talked about mapping X's to Y's, but then here I'm talking about Q's and V's and K's. I'm going to come back to the issue of building Q, V, and K a little bit later on. But to summarize basically what we have at the moment, we have here this is our attention, our basic attention unit. The inputs are values, a list of values, a list of keys, and a list of queries. The value and key sequences have the same length, n in, but they have different dimensions, dv and dk. The Q is going to have a different length, n out, but because we're using dot product attention, that means Q and K must have the same length. So that means that dq is equal to dk. And this is the unit that we're going to be using from now on. It's easy to recognize the complexity here. So the complexity is going to be dominated by this term here. So we have n out A's, we have n in I's, and we have dk values here. So our complexity is going to look like this. So for standard attention, if your sequences are of length n, then your complexity per layer is going to look like this. Okay. So far I've talked about how you can map one sequence to another sequence using the attention mechanism. But there's an important issue, and that is once we've taken our vectors, where are we? This is the question of positional encoding. So what I mean by this is when we apply the attention maps to convert one sequence to the input sequence, the output sequence, that means that we take these values, we compute a digest, we smash all the results together. We get some result for our query. However, once we smash all of these together, we don't know where each individual component, we don't know where the different pieces came from. In a sequence-to-sequence task, the order of elements is extremely important. And that means that if we're going to use attention to handle sequence-to-sequence tasks, then we're going to have to include that information in the vectors that we input into the model. This procedure is called positional encoding. And the method that's used in this paper is sine and cosine encoding. So what you do is so pause here represents the index in the sequence. And then you have a collection of labels I, which goes from 0 to D model minus 1, or 1 to D model. And so these quantities here will then generate some D model number of components. D model here, that's the dimension of the vector space in which each of the model stages, that's the dimension of the input and output dimensions in each of the model stages. So that means that if we have a collection of input vectors, X, the X vector at position pause, this lives in the model vector space, our D model, then its positional encoding is done just by taking the original vector and adding in this positional encoding vector whose components are given by this equation. There are alternate versions of encoding. You can use a learned encoding learned encoding scheme. But they found that this performed just as well, and it has the advantage that your model will be able to deal with longer sequences than appear in the training data. Okay, related to the issue of localization is the following issue. So if we have a single attention layer, and we have something like this. So let's say that we have the attention is going to focus on some region of the input. However, at a given stage, you might actually have multiple regions that are relevant. So for example, if you have a sentence, you don't have a single simple noun, but instead your noun consists of the Queen of England or some other compound thing. You have to, and in order to understand that component, you have to put together pieces located in different places. Right. There is an inherent tension in this case between the spatial localizability of your output results and the expressiveness with which your output can capture properties of the input. So because the positional information is just sitting in the vector, if you superimpose stuff coming from lots of different places, then you're also going to be superimposing positional information. And that's going to reduce your ability to localize where that information came from. Now, on the other hand, if you focus on just one piece, then you can maintain good localization information, but you're going to lose the ability to match components, disparate information from disparate locations. So in order to address this tension, the paper introduces the multi-headed attention module. So in the multi-headed attention module, what we do is, so given our whatever values, keys, and queries that we're interested in applying attention to, what we do is we first split them into smaller bits. And this is going to be done via a linear map. So this is because, so each of these components here is going to go into a different attention head. We don't know a priori which attention head is going to want to know about which type of information. So what we do is this here is going to represent a linear mapping from the model vector space to a value vector space. And this is going to be a learned weight of the model. So this learns what values are relevant to this head. Similarly, right. So then the value is going to be split into these different pieces, each of which are going to encode different bits of the original value tensor, and they're going to be fed into different attention heads. Similarly, we do exactly the same thing with the keys and with the queries. So these attention heads are then going to learn to focus on somewhat different pieces of information, and that will allow us to maintain localizability while still being able to consider conceptually distinct pieces of information. Finally, we have, for each of these attention heads, we're going to have an output vector, and these have to be collated into a final output vector. And that's done by another linear map. So we take these three outputs, we concatenate them, we apply a linear map, and we produce our final output vector. So in everything that follows, this symbol is actually going to refer to this entire multi-headed attention module, including all of the linear map weights that are hidden inside these components here. Okay, so now we have all of our ingredients. It's time to actually put things together into a model. So the overall architecture of the model is a standard encoder-decoder architecture. During training, what we're going to have is we're going to have two different inputs. We have the input that the model is going to use as a basis for inference, and we're going to have the target output, the desired output. Now, given an input sentence, we need to then convert these into vector sequences, into sequences of input vectors of dimension D model. And the way we do that is we use some type of input embedding. You can use a prepackaged scheme like Word2Vec or something, or you can build your own. But the important thing is that you have some map from input tokens to a sequence of input vectors. And of course, you need that also for your target language. Okay, so the next thing you do is you perform positional encoding. So as I said, so here our input embeddings are of dimension n in, so we have n in vectors of dimension D model. The positional encoding, for each position, you get a vector of dimension D model. So that means that the tensor that's being output here is the same shape as the tensor that's being output here. You can just add these together. So that is the information that is going to go into the encoder. And similarly, exactly the same procedure is going to be happening as we go into the decoder. So let's look at what happens in the encoder. So the encoder, the core of the encoder is multi-headed attention module, which lives here. Now, the important thing to note here is that we have one input coming in, and this is just being sent to all of the three inputs, V, K, and Q, to the attention module. And this is known as self-attention. So this in self-attention, because the same vector X represents the same sequence of vectors, X represents the query, key, and vector, we're asking the tensor X what parts of the tensor X are relevant. So we're asking it basically to pay attention, how it should pay attention to itself. We put that through self-attention, we're going to get an output sequence. Now that output sequence, because our query is the same sequence of vectors X, that means that the dimension of the output tensor is going to be the same as the dimension of the input tensor. It's going to be n by D model. And as a result, we are also free to add a residual connection here. This will help our model to train more quickly, to not have problems at early stages of training. Then we add a layer norm to help keep the model from blowing up. And then we add this dense bit here. So what I mean by dense here is that we have a dense feed-forward network consisting of 2 layers, and that network is time distributed. So at each stage in the sequence, we apply the same network. So in this case, we apply the same network n times. This network has plays a couple of important roles. So one thing it does is it takes, given these output vectors from the attention, it's able to collate the information to extract more detailed, more complicated features from the superpositions of vectors that we've generated in the process of applying attention. In this particular architecture, you first feed each vector into the hidden layer, which is much larger. So in the paper, they choose D hidden to be 2048. And then this is fed into a second stage, which maps it back to the dimension of the original model. And they chose this to be 512. And between these two, there is a ReLU activation. So that helps to extract more complicated, more nuanced features from the output of attention. And then finally, we have a residual connection and we have a normalization layer. So this is all pretty standard. That is all pretty standard stuff. One attention layer is not going to be enough. It's simply not enough to generate good features on which to base a translation. So as a result, this entire block here is going to be repeated some number of times n. And they chose the number of times n to be equal to 6. Now let's look at the decoder. Now the decoder differs from the encoder in 2 crucial features. So let's begin with this bit down here. So this so far looks the same as this over here in the encoder. We have self-attention, same input tensor going to all of V, K, and Q. However, this has to be a masked self-attention stage. And the reason for this is that let's say that you're trying to compute, you're trying to predict this output sentence, and you're looking at position 2. And let's say that position 2 knows, for example, what the key was from position 5. Well, that means that it gets prior information about parts of the sentence that it hasn't learned to generate yet. And even worse, if Q2 could see, if the query at position 2 could see the key at position 2, then it would already see the input, and the model wouldn't learn anything. So as a result, you have to make sure that Q2 doesn't see anything at position, any keys at position 2 or after. If we're looking at position 5, then Q5 could see positions 1 through 4, but it couldn't see position 5. So this can be done just by setting the relevance score to a very negative number whenever the key comes at the same position or after the query. Okay, so that's difference number 1. Difference number 2 is the obvious feature that we have a second attention layer here. And this, of course, is the powerhouse of the entire architecture, because this is where we take input from the encoder, we take input from our input language, and then we try to use it to compute something that goes into our output language. So notice the structure here. So here we have an output, embedding vector running through a model. And that vector is going to know things like what is the position of the current token that you're trying to predict, what has been predicted, or what words appeared earlier in the sentence. And that information is relevant in determining what you should pay attention to coming from the input language. So in this case here, if you're trying to do position 2, then you probably know that you're looking for a verb, but you don't know what verb you're looking for. In order to figure that out, you need to bring in information from the encoder. So that means that our task is set by our query is set by the state of the output tensor, the decoder tensor. But the information that it's going to be using to check for relevance, the keys, and the values that we actually want to use in order to produce our outputs. So both key K and V should be coming from the final output of the encoder. Notice we also have this residual connection here. So this guarantees that we preserve all of the information that's coming from, that we've managed to extract from earlier stages of the decoder, and we are able to update it with additional information coming from the encoder, which is relevant to the query at this stage. Finally, we have a norm. We have the same type of dense structure. We have residual connection, and we have a layer norm. So this is the basic encoder decoder architecture, and this is where attention is appearing inside this translation model. Like with the encoder, the decoder also it's not going to suffice to use just one self-attention and one attention layer. We're going to have to stack up a bunch of different attention layers, each of which is getting an input from the encoder. So we're going to take this entire block, stack it n times, and in the paper they set n to be equal to 6. Okay, then the final step when we're producing output from the model is, of course, we need to go from our vectors. So here, here, and here, and here, we have vectors of dimension d model. So here we're going to have an output of length n out, which has d model dimensions. And that has to be converted into actual words. So we first provide a linear map, which maps us to weights on the space of possible output tokens. And then we apply softmax in order to convert those weights into probabilities for each individual token to appear at each individual stage in the final output tensor. When you're running inference, of course, in the encoder-decoder architecture, you have to change things change a little bit because you don't have a complete input sequence to begin with. So when you're performing inference, and this is standard encoder-decoder architecture translation stuff, but you start with your initial input is just going to be the token begin. This tells us that we're going to begin a sentence. We perform positional encoding on that. You push this into the decoder. You get inputs from the encoder, and the decoder is finally going to spit out an encoding of word number 1. That's the first word that comes after the begin token. Once we've done that, we take that output, we bring it back here, we tack it on to begin, and now we have a 2-vector input. We input this, and then we run the decoder. We use the inputs from the encoder, and we produce our next output element. And then we can repeat that process until we finally produce a terminal terminal symbol. And at that point, we have the end of a sentence, and we have performed inference. So, given this model, how well does it perform? Well, they evaluated the model on the BLEU test for both the English to German and the English to French translation tasks. And you can see here that not only was the best performance for both these tasks produced by the transformer models, but in addition, if you look at comparable performance with other models, so for example, this base model, you compare it to this Conv S2S model, you can see that the training cost for the Conv S2S model was considerably larger than the training cost for the transformer base model. So that means that they managed to accomplish their goals, which were getting good accuracy and doing it in a computationally efficient fashion. So as a result, it turns out that in order to perform neural machine translation, attention is all you need. There are a number of important details I didn't cover here in great depth because of time constraints. The encoder-decoder architecture I kind of fluffed over, and that was handled in more depth, I think, in a previous talk. But I hope that this has given you a picture of what attention is and how you can use it in order to perform effective machine translation and other sequence-to-sequence translation tasks. Thank you very much for your attention.